if we have a function f of x, y, its graph, of course, is represented as a surface above the xy plane, well above and below and on. So that a typical point on the graph corresponding to values x naught and y naught would have coordinate x naught, y naught, f of x naught, y naught. So here's the point x naught, y naught, 0. Here's the point x naught, y naught, f of x naught, y naught, directly above the xy plane on the graph of the function. Now, if we hold x constant, then, I've got an arrow on here. I'm going to get rid of that. I wasn't sure I liked it before. I'm pretty sure I don't like it now. This is a line, x equals constant, down in the xy plane. So we're holding x constant. Now, in 3 dimensions, x equals constant. If the x-axis is this way and the y-axis is this way, then x equals constant is a plane like this, parallel to the yz plane at whatever the value of x is. So you come out to that point, that x value on the x-axis, and your plane cuts right through. And of course, it cuts right through the graph, so your graph is going to have some shape within that plane, and it's going to be just a curve within that xy plane. Now, it's a surface when you look at it in 3 dimensions, but when you cut it with a plane, it's just a curve. So the function that you get within the xy plane, if x equals x naught, because this is an x equals constant plane, and we're assuming this is a point x naught, y naught, 0, y is changing here, but x isn't. So your f of xy function will be confined to the one single x value, x naught. That isn't going to change. So there's just going to be a number that you would plug into the formula for x naught, and now you have just a function of y. So f of x naught y is just a function of y, and z equals f of x naught y is just a z versus y function within this plane. And that's what your curve shows you. The slope at this graph point, x naught, y naught, f of x naught, y naught, is just the partial derivative of f with respect to y, evaluated at the point x naught, y naught. And that's just going to be, again, the slope of this graph within the x equals constant plane, a plane parallel to the yz plane at this point. Now the question becomes, what we're really trying to build up is the equation of the tangent plane to the whole surface at this point x naught, y naught, f of x naught, y naught. So in order to do that, and you'll see why in a minute, we want a vector that has the same direction as this tangent line, because of course that vector will be parallel to our plane. Now we're going to do the same thing holding y equals constants. We're going to get a plane coming out this way, and we're going to have some curve in that plane, and we're going to get another vector, and those vectors will both be parallel to the plane, so the cross product, being at right angles to both vectors, will be normal to the plane. So we're going to get our normal vector. We've got our point. If we've got a point in the normal vector, we easily get our plane. So, task then is to find any vector that has slope partial of f with respect to y as evaluated at x naught, y naught. In other words, a vector with this slope. Well, we come over here, and it took us a while to get this. So this is something you see, especially like when you do arc length in first year calculus. And everybody will have seen this, but it doesn't always lock in, just like everything else in a challenging course. It doesn't lock in until you see it a second time, or just like many things, a lot of things do lock in. This is one thing that might or might not have locked in. So we want a vector whose slope is m. Okay, and what that means is that this vector in the yz plane is in a direction where the slope would be m. So the rise divided by the run would be m. Well, it took us quite a while to get this, okay? you know, I first ask, okay, if v equals some multiple of j plus some multiple of k, then give me a multiple of j and a multiple of k so that your slope would be m. Now, I think maybe the question marks confuse people. So I ask, okay, let's use symbols. If it's aj plus bk, remember this is a vector in the yz plane, so you have a j and a k component to any vector in that plane. What's the slope of that vector? Well, slope is rise over run. Rise is in the k direction, run is in the j direction. So it doesn't take too much to see that the slope of that vector would be b over a. Okay? Now, if the slope is m, then b over a equals m. So all you got to do now is give me two values for a and b such that b over a equals m. Okay, so somebody said, okay, how about 3 and 3m? Just let a equal 3, and then you conclude that b equals 3m, right? b over a equals m. So first vector I got was 3i plus 3mk. Perfectly good vector. And it does have slope m. Then I pointed out that, well, really the easiest thing to use for a would be 1, wouldn't it? So if a is 1, b is a. So the vector, and from that you would get the vector j plus mk. Rise would be m, the run would be 1. Easiest way to get a slope of m, let the run be 1, let the rise be m. Okay, and you want to lock that away. That's really important for arc length integrals and a lot of other things. Okay, well, now we've got our vector. Of course, the slope m, in this case, is our partial derivative, because the partial derivative is the slope of this tangent line. So the vector could be j plus your partial of f with respect to y at x naught y naught times k. And we could get a unit vector. And it turns out that I really kind of didn't want to do that. Okay, but I did. So we get a unit vector, and that's what the unit vector looks like, but it turns out that something doesn't work out the way I was thinking without thinking it through that it would. Okay. So we could use this unit vector, but we could just use the j plus partial f with respect to yk. If we do the same thing in a y equals constant plane, in other words, this would be the plane,
right here.
just as this is the plane x equals x naught, because it's the plane x equals x naught that goes through this
That's what I was,
point,
okay, that's what
the
I was thinking.
vertical
And
plane,
then, see, we moved the stuff around just a
for
little
constant
bit.
x that goes through this point. This would be y equals y naught, the y equals y naught plane. And we'd get a curve in the y equals y naught plane, and people had no trouble saying, okay, well then the slope would be the partial with respect to f, to x, evaluated at x naught, y naught. So the partial with respect to y at this point gives you the slope of this thing. The partial with respect to x at this point gives you this slope. And the vector with that slope, it's easy to see once we've seen this, it's just going to be 1 in this direction and slope in this direction. In other words, I plus partial f with respect to x, k. Now, I just wrote partial f with respect to x. I didn't want to write out evaluated at x naught, y naught, but that's implicitly the case. And then if we wanted to write the unit vector, well, I went back to writing the x naught and y naught. So we have these unit vectors, where now I've written just plain fy instead of partial of f with respect to y, and understand that this is fy evaluated at our x naught, y naught. So we have this unit vector and this unit vector. Both of these vectors are parallel to the tangent plane, so the cross product, you can't read that prod, but that's what it says. Cross product is the unit normal, and that's wrong. It really isn't a unit normal, so there's no point in making these unit vectors. And we saw when we got here that it wasn't a unit normal. So I'm not sure what I was thinking. Okay. So that's the strategy for finding a normal vector, and we know how to find the equation of a plane if we know the normal vector and a point on the plane. Now if we have our function f of xy, we know the coordinates of this point, and take the cross product of these vectors and we get a normal vector.